In this video, we're going to learn how to solve higher order constant coefficient differential equations like this one, y triple prime plus y prime is equal to 0. So what do all those words mean? So first of all, what type of object are we studying? I said it was higher order, and that's because of this y triple prime that I have here. The order of this differential equation is 3. And then the second point is that this is a constant coefficient differential equation because the coefficient of y double prime and the coefficient of y prime are both 1. You could also imagine that there was a y double prime and a y here, but those just have coefficients of 0, which are also constants. Now the methodology to solve this is very similar to the methodology that we've used previously to solve second order constant coefficient differential equations like this one. So what we're going to do is we're going to guess a solution of the form y equals e to the r times t. And if you were to substitute that in, you get a so-called characteristic equation. Well, 3 derivatives of this is going to give you an r cubed times an e to the rt, which we'll cancel in a moment. 1 derivative of this is going to give you an r times an e to the rt, which we'll cancel in a moment. And then this is equal to 0, canceling out the e to the rt's. You're just left with this, the so-called characteristic equation. Now, what's relevant here is that this is a polynomial. Now, if you had a degree 2 polynomial, you can always solve this by the quadratic formula. So any degree 2 polynomial you could factor, and we've seen that there have been a few different cases. You could have 2 different real and distinct roots, you could have real repeated roots, or you could have a complex pair of roots. So what's going to happen in the third order case? Well, first of all, I can sometimes factor these, but I have to be a little bit more ad hoc about it. Namely, I'm going to just observe that I could factor out a copy of r, and that would leave me with r squared plus 1. And then I could do even further if I looked at that r squared plus 1. Well, that doesn't factor nicely over the real numbers, but it does over the complex numbers. So this could be thought of as r times r plus I, and then multiplied by r minus I. I can factor that over the complex numbers. Or, if you prefer, I could do the quadratic formula on r squared plus 1, and that would give me plus or minus I as well, whichever you prefer. By the way, it's kind of cool. For the quadratic formula, we can always solve them. But what about, say, cubic and quartic polynomials? Well, it turns out that you can also always factor a cubic and a quartic polynomial. There is an analog of the quadratic formula, but it is just much, much more complex and challenging, and so we don't typically teach it. However, for degree 5 and above, there is no sort of solution that always works, no methodology that always works to be able to factor them. So the general methodology is to guess one solution, like we guessed the r was one of the solutions here, and factor it out, and then you're reduced down to something that hopefully you can do. Okay, so what do I have? Well, from this characteristic equation, I see now that I have 3 different roots. r1 is equal to 0. I have r is equal to minus I, that's r2, and then r3 is equal to plus I. And then since our solutions were of the form e to the rt, my general solution looks like this. It's some generic constant c1 multiplied by e to the, well, r is 0, so 0 times t, and then a constant c2, e to the minus I times t, and then finally c3e to the plus I times t. This answer is okay, but I want to do 2 different manipulations to it. So the first manipulation I'm going to do is, well, I'm just going to say that e to the 0t is just 1, and so I'll just put the c1 out the front. That's the easy manipulation. But then the second manipulation I want to do is I notice that I have this 2 different exponentials with imaginary numbers in them, e to the minus it and e to the plus it. Now, my goal is to take these exponentials with imaginary components, and I would like to have 2 real linearly independent solutions I can use instead. The standard trick, exactly as we did when we were talking about the second order case, is that if you have e to the, say, alpha plus or minus I beta times t, that would be the general case, then your 2 different solutions are e to the alpha cosine of beta t and e to the alpha sine of beta t. And the details of that conversion we did in the previous video. So for the purpose of our example, I'm just going to say c2, well, my alpha is 0, there's no real component, and my beta is 1, so it's c2 times cosine of t plus c2 sine of t. And that is my final answer. All right, so what have we done? For our original differential equation y triple prime plus y prime equal to 0, we now have this general solution c1 plus c2 cosine and c2 sine. All right, so that was one. Let's do one more example to lock in what happens when you have multiple types of repetitions. So the second example is actually a fourth order constant coefficient equation this time. It's the fourth derivative of y. When you put it in brackets, you don't mean to the power of 4, you mean 4 derivatives. The fourth derivative of y minus 3 times the third derivative of y plus 3 times the second derivative of y minus y prime all is equal to 0. Okay, a big mouthful. So we'll come up with our guess, as we always do for constant coefficients, y equals e to the rt. And this is going to give us our characteristic equation. Well, 4 derivatives gives an r to the fourth minus 3r cubed plus 3r squared minus r is equal to 0. All of these terms would be multiplied by e to the rt, but because they're all multiplied by e to the rt, I just cancel it. That's my characteristic equation. So now we turn to the question of trying to actually factor this. How can I do that? Well, perhaps the first thing I'll observe is that similarly to what we had before, I see that r equal to 0 is a solution. And so I can factor 1r out, so that gives me r cubed minus 3r squared plus 3r minus 1 is equal to 0. I've made a little bit of progress. Now I have a cubic polynomial that I want to factor, multiplied by r. So how do I factor this cubic polynomial? Now, one thing you might just have an alarm bell going off in your head is that the numbers of 1, 3, 3, 1, that looks a lot like Pascal's triangle. If you know what I'm talking about, you'll recognize that pattern. And if you don't, that's totally fine too. You can look at this and try to find one solution, and I'll just observe that if I plugged in r equal to 1, well, that would work. Plugging in r equal to 1 would give you the value of 0. And so you could factor out r minus 1, and what you actually get is the following. This is r times r minus 1 cubed is equal to 0. So again, I just sort of recognize this pattern because I've seen it before with Pascal's triangle, that r minus 1 cubed, if I wanted to expand that, would have those coefficients of the 1, 3, 3, 1, possibly with some signs. Or alternatively, you have to sort of guess and find that solution of r equal to 1. If you factor it out, then what you'd be left with, you'd be then able to do with the quadratic formula. Regardless, I have this. Okay, so now looking at what I have the following problem. I have one root here, which is r equal to 0. And I have a second root here, which is r equal to 1. But the problem is it's r equal to 1 cubed. And so the way I think about this is with what we call multiplicity or repetition. But it's multiplicity 3. So it's repeated 3 times. So the issue is, I can't just go and say that my solution, which I might be tempted to do, would be like c1 e to the 0t plus c2 times e to the t, that would be with r equal to 1. But because it's degree 4, and I'm looking for 4 linearly independent solutions, I can't just go along here and say that c3 is e to the t again. This just doesn't work out. The reason is that that is just a copy of the term that I already have. This is not a new linearly independent solution. So what can I do? Well, the methodology of repeated roots is that you can multiply by extra powers of t and it still works out. So for example, I'm going to take c3 and I'm going to take the e to the t as I was anticipating, but I will make it t times e to the t. And then in addition, I will have a c4 and an e to the t as you'd expect, because this is the third time that the root of r equal to 1 repeats, but I'm going to put a t squared in here now. And in general, if it repeated 10 times, you'd be going all the way up to a t to the 9th times e to the t. It just depends how many times it repeats. Either way, this is now my general solution when I have this repetition. So let's zoom out for a moment and try to think about how I solve all of the different ones of this category. That is higher order constant coefficient differential equations. Well, I'm going to plug in the e to the rt. I'll get a characteristic equation, and that characteristic equation can be factored as it's a polynomial. How I factor it might be a little ad hoc in the higher dimensions, because I can't just use the quadratic formula to always do it. I might sometimes have to guess a number that I can factor out. But regardless, at the end of the day, you have a combination of distinct real roots, repeated real roots, and complex pairs. No matter what the polynomial is, it will always look like that. Some number of complex pairs that could be repeated, some number of real roots that could be repeated, and then of course distinct roots. And then you take all those roots and you put them together into your general solution in exactly the method we've seen here. When it repeats, you might need to multiply by a t at the front, and when it's complex pairs, you might want to convert to cosine and sine. And if it's just distinct, then it's easy. You just put the different exponentials in. No problem there. Okay, so the part I haven't really told you yet about is some of the more theory side for higher order differential equations. We're going to do that in the next video. We'll talk about existence and uniqueness. We'll talk about why it is that we're looking for an nth order differential equation. We're looking for n linearly independent solutions to that differential equation to form my general solution. What do I mean by linearly independent? We'll more precisely talk about those concepts all in the next video.